Hey everybody, here's an example where we're going to use differentiation to find a power series representation for this particular function here. So again, the only one we have at our disposal at the moment is the geometric series. So geometric series we have, let's say g of x is 1 over 1 minus x. We know how to represent that using our good old-fashioned geometric series. Okay, and obviously, this is with the interval of convergence from -1 to 1. We've talked about that, but this is the actual series representation for this function, which does have a relationship to the one they're asking for. They're kind of giving you the hint in the question by simply saying use differentiation, but that's what we had talked about in class. So if we take the derivative of this series, if we actually even look at just the terms, might make it even easier to see what's happening. If we go to take the derivative of this, well, we can just do a power rule, chain rule here to figure out that this derivative is 1 over 1 minus x squared. I'll leave that for you to double check. And look at the terms, right? Here, I'll just start with the terms, and then we'll develop the series itself. The derivative of 1, of course, is 0. X is 1. X squared is 2x. X cubed is 3x squared, etc. And that is going to be the series n x to the n minus 1, starting at, if we want our first term to be 1, we'd have to start at 1 here. Okay? And that would be the power series representation for this function. Now, I know in the book sometimes they shift it here or there. Sometimes they'd like to have their x, term just to the n power. So we could rewrite it if we wanted to. And in the book, it even says if we like, in the example they do. So either you like or you don't like. But if you want to make it match what they have, then we have to like. So this one, if I want to shift it to n equals 0, this would have to become n plus 1. And then this would become x to the n. And it's easy to check if you just check the first couple of terms. If n is 0, this is 1, x to the 0, so 1. If n is 1, this is 2, x to the 1, 2x. If this is 2, this is 3, x to the second, which is here, etc., and both of them will work. So that's just manipulation. But to get here, we did take the derivative. So I did it term by term. Here, this term actually goes, technically there's a 0 in front, but I'm not going to bother writing it. So derivative of x is 1, x squared is 2x, etc. Becomes this function here, which is the derivative of the original geometric function, the sum. And it looks almost like the one they gave us with one little exception. This is 1 plus x instead of 1 minus x. So we could rewrite this one very simply as 1 over 1 minus negative x quantity squared. Okay, so now I'm basically looking here saying, how can I make, this look like that? Like what little twists and turns can we do to manipulate it just a little bit? So that's what we've got, which means this series can be rewritten just like this series, and take your pick. I'll just use this one. I can do it n equals 0 to infinity, n plus 1. So instead of x to the n, I have negative x. So it's going to be times negative x to the n. And then sometimes they'll actually split up when there's an alternating portion, like this negative here. So this is really negative 1 times x, and both of them are to the n power. So I'm just going to split them up. So we have negative 1 to the n plus 1, x to the n, right? Negative 1 to the n, x to the n. If I put those back together, I'll get back to here. And this is a power series representation for this function. If you were to list out a few terms here, graph it along with this graph, it'll be accurate over its interval of convergence. I think this one actually does ask for the radius of convergence, so we could just quickly figure that out. Well, this is our, x to the n term here. So as long as the absolute value of x is less than 1, our radius of convergence is 1. Interval will be between -1 and 1. And I think we've successfully completed that problem. Okay. In the next video, I'll do what happens when we have to do it again. But this is the intro for, I believe this was 13A from our book of finding the power series representation using differentiation. So hopefully that helps. If not, be sure and let me know, and I'm happy to try again. Okay, see you later.